Okay, so in the previous video I explained the basic idea, statistical idea of hypothesis testing. So let me summarize the basic steps. First, you have to define the hypothesis in terms of statistical parameters, right? So you use parameters and usually it's given like this. Second, you have to choose how strict or how generous you will be, right? That's the significance level, right? The probability below the significance level will be ignored. You are not going to believe that probability. Third, now collect data and calculate a test statistic that you are going to rely on. You are going to rely on this statistic, the value of this statistic. So in the end, you are going to reject or accept the null hypothesis based on the realization of this test statistic. And theoretically, what you need to do here is you assume that the null hypothesis is correct, your belief is correct, and then calculate how this statistic would be distributed. Like, for example, X bar is a typical choice, and you know X bar is normally distributed approximately by the central limit theorem. And what you have in mind here is, okay, if your belief is correct, then you may be able to calculate the mean and variance for the normal distribution of X bar. That is called the null distribution, right? And then suppose that you calculate a certain realization from the data. Then what I'm going to calculate is I will calculate the probability of less likely values or more suspicious values of the test statistic than what you observe, right? So you are calculating the ranking of suspiciousness from your observation, right? That is called p-value. So the suspiciousness is expressed as a probability, 0% being the most suspicious and 100% being the least suspicious, okay? So that is based on the null distribution. And finally, if the p-value is too small, then you are going to ignore that. So you are going to reject if the p-value is too small. If you decide to reject 5%, significance level is 5%, that means if the p-value is smaller than 5%, you are going to reject. So the ranking is close to 0. It's too suspicious, so you are going to reject the null hypothesis. Alpha is the cutoff. Alpha is the threshold to make the decision. Okay, that is the basic flow of the hypothesis testing. And a few key terminology here. Test statistic is a statistic that is calculated from the sample and is used to determine whether to reject the null hypothesis. You are going to use this to reject. And the null hypothesis is the sampling distribution of the test statistic if the null is correct, right? And the p-value, technically it is the probability of test statistic taking more unlikely values than the observation. But I would interpret this as the ranking of the suspiciousness, right? Express suspicious outcomes in terms of probability. And significance level. This is the threshold to determine whether to reject the null or to reject the null hypothesis. So you are going to compare the p-value with the significance level. Okay. So let's think about more concrete example. Study hours. I believe that you spend a lot of time on studying for the midterm exams. So in the past midterm exam period, I believe that students at Albany spend 30 hours, say, per week to study for midterm exams on average. So average is 30, I believe. So to test my belief, I asked 100 students midterm exam study hours, right? And the sample mean was 31 and the standard deviation was 10. So I believed student average was 30, but it is slightly greater than that. So then there are two ways to think about that. Okay, the sample mean was 31, which is different from my belief. So my belief may be wrong. The true mean was 31, so I underestimated you guys. Or another thing here is the difference between the observation and my belief could be just a random error. Excuse me. The true mean is I am correct. Suppose I'm correct. 30 hours is the true mean, but in the survey there is randomness, right? I just happened to meet students who studied a lot more than the average. So plus 1, the difference plus 1 is a random error. If I survey again, then I may get another different number like 29. So that is possible. So we need to determine which is correct. We can think about the difference in this difference can be understood in two different ways. Either my belief is wrong or the observation is a random error. That's two basic ways to interpret the difference. And finally, I choose 5%, which is standard. So that is my threshold. Not too strict, not too generous. Okay, so step 1, define hypothesis. So mu is the true population mean, and I believe that is 30 hours. So here, underlying random variable is the midterm study hours. When I randomly choose a student, X is her hours of study for the midterm exam. Okay, and mu is the population expectation of the random variable. Okay, I already chose the significance level, and I choose X bar as the test statistic. Because, so by the way, remember that the X bar, the sample average, is the best point estimator for the population expectation. That is what we learned in the previous chapter. Similarly, test statistic plays a similar role as an estimator. So we are going to use X bar as the test statistic here, right? Because we are testing about the population expectation. So it is natural to calculate the sample mean from the data and use that as the basis of our decision. And here, now theoretically, I'm going to think about the sampling distribution if my belief was correct. So I believe the true population mean mu is 30 hours. So the central limit theorem tells you the sample average follows approximately normal distribution with these two parameters. And based on my belief, if my belief is true, we know mu is 30. But my belief does not tell me anything about the variance. Sample size is clear, 100, it's given. But the variance must be calculated from the data. So the data we know from the data, we know that the standard deviation is 10. So even though we obtain sample mean from the data, we do not use this because it is replaced by the belief. Belief is more important still, right? But standard deviation is used because my belief does not say anything about the standard deviation. So when there is no option, then use the data. But if your belief has some information, use that. That is the rule, okay? So anyhow, then you can theoretically you can show that the sample average will be normally distributed around 30 hours with the variance like this, right? So it looks like this, centered around 30, and dispersion is based on the data. And here, in this case, I would say my belief is less likely to be true as the observation goes this direction or in the opposite direction. Okay, so my belief is most likely to be true if the observation is close to 30. As my observation is further away from 30, then my belief is suspicious, less likely to be true, right? So I colored this way. So in other words, I am going to reject my null hypothesis if the observation is too small or too large. In other words, if the observation is too much different from 30, I'm going to reject my null hypothesis. That is what we are going to learn from the graph and this color, this gradation. Okay, so far it is purely theoretical graph, but from the data, we know the realization is here. My realization is 31. Okay, then what we are going to do is we are going to calculate the ranking of this observation by calculating this area. Here, of course, I have to calculate this area. So, for example, my observation is 31st. So, any number greater than 31st is more suspicious, right? That is obvious. But also, what you have to keep in mind is the other side. So, 29, a random error of -1, is as suspicious as +1. So, we observed +1, like my belief +1, but +1 is statistically equal to -1. So we have to treat these guys like more suspicious than my observation. So basically, I observe like the difference from my belief by 1. The difference was 1. So what I'm going to calculate is the probability of observations with difference greater than 1 from 30. That is this area. And that is called p-value in hypothesis testing. Okay? So then it is clear. Like if your observation is further away from 30, like now it is +1 -1, but if it was like 32, then your observation will move away from 30, from the center, and the tail probability will be smaller. So p-value will be smaller as your observation goes to the tail. So as observation goes to the tail, your hypothesis will be less likely to be true. That is natural. That is, the smaller the p-value, the more suspicious, right? The less likely to be true your belief is. That is what you can see here. Okay, then mathematically, p-value can be written this way. P-value is the probability x bar, the test statistic is greater than your observation or smaller than 29. So this is the counterpart of your observation to the other tail, right? Because +/-1 has the same difference from the belief. So we are going to include two probabilities. Then how can you calculate that? Use the standardization. You know how to do it. So x bar is normally distributed. So standardize like this and like this. Subtract the mean, divide by standard deviation. And again, remember the mean is based on the null hypothesis. This is not based on your data. So the mean, the population mean here, this parameter is 30 because you believe the data more than your data. Excuse me. You trust your belief more than the data. Still, until this point, right? So you get this, then in the end, your probability, your p-value is standard normal distribution smaller than -1 or greater than 1. And according to Excel, you can obtain that probability is 31%. This is not that difficult. Calculating this, once you understand what it means, then calculating that probability is straightforward. We did a lot of practice to do this. Okay, so so the main point is you need to you need to rely on your belief more than the data first, and if the belief does not say anything, then go back to your data. That is the basic principle. So the null distribution is based on that assumption. And here you may just treat this standardized value as another statistic. So we usually call this small t, student t statistic. T statistic takes this form, right? So your observation is 31, and if you standardize that, it will become 1. That is t statistic. Student t statistic, and you may calculate p-value directly from the t statistic, right? This is another way to define p-value. So skipping the standardization process, because that is automatic. So standardize your test statistic directly and then plug the result into here. So by the way, here I take absolute value because the standardization may be negative. But even when it is negative, still you have to calculate probability greater than the positive counterpart and smaller than negative counterpart. So outside plus minus t statistic. Okay, that is the p-value. Okay, so then we just calculate the p-value, which is 31%. And at the beginning, the significance level was chosen to be 5%. So now compare that. So you may interpret it this way. So as I said, from the data, I find a difference of 1. The observation is 1 hour greater than my belief. So then this difference can be caused by 2 reasons. First, your belief may be wrong. Second, it can be just a random error, right? So what I'm calculating here is for this random error to happen, the probability is 31%. So the random error can happen with this much probability. And this probability is reasonably significant, right? It survives when we compare that to the significance level. So, okay. So, that is pretty good significant probability. So I would not change my belief, but just I will interpret the difference as a random error, because the random error is pretty much likely to happen. It's 30%. Okay, that's a good probability, reasonable probability. So we cannot reject the null hypothesis. Even simply speaking, because p-value is greater than the significance level, we cannot reject, right? Oh, in another word, remember the p-value is ranking. So when you rank from the most suspicious to the least suspicious, your observation is only at top 31%, which is not that high relative to the significance level. So it is not that suspicious. So you don't reject the null hypothesis. That is how we are going to interpret this. Okay. So this is a numerical example how we implement the null hypothesis testing and how we can interpret each part of the framework. Okay. So in the next video, I will discuss a little more general format, and then we'll discuss the decision rules, more specific decision rules. Okay, thank you for watching. See you later.